to solve some of the good problems of this paper, and the first question I am going to discuss is question number 8. An electron in a hydrogen atom in the second excited state jumps to the first and ground state of the atom. Find the ratio of the wavelengths emitted during this process. I am going to use the Rydberg's formula 1 upon lambda is equal to r 1 by n final square minus 1 upon n initial square, where r is the Rydberg's constant. For transition from the second excited state to the first excited state, 1 upon say lambda 1 is equal to r 1 by 4 minus 1 by 9, that is equal to r 36 9 minus 4, that is equal to 5r by 36. This implies that lambda 1 is equal to 36 by 5r. Similarly, for transition from the second excited state to the ground state, 1 by lambda 2 say is equal to r 1 minus 1 by 9, that is equal to 8r by 9. This implies that lambda 2 is equal to 9 by 8r. Therefore, the ratio lambda 1 upon lambda 2 is equal to 36 by 5r into 8r by 9. 9 for the 36. R get cancelled, and this is equal to 32 by 5. This is our answer. Question number 9. There is a regular hexagon. 5 plus q charges are placed on 5 vertices like this. There is a minus q charge at the center. Since opposite charges attract each other, all these positive charges will attract this negative charge towards themselves. Since these are equal in magnitude and opposite in direction, they will cancel each other. The net force on this negative charge is only due to this positive charge, whose magnitude is given by kq square upon this distance. Since this is L, this is 60 degree, and this triangle is an equilateral triangle, this is also L. So our answer is kq square upon L square. In the optional question, we have to calculate time period of a simple pendulum in a vertically downward electric field. Let the simple pendulum be displaced through a small distance x in the tangential direction. This angle is theta and this is L. The force on the pendulum in the vertical direction due to electric field is Q times E. This angle is also theta, so the component of this force in the tangential direction will be QE sin theta. So we can write F is equal to minus QE sin theta. Negative sign shows that the force is in the opposite direction to the displacement. This implies that MA is equal to minus QE sin theta. This implies that A is equal to minus QE by M into sin theta. If theta is very small, sin theta is approximately equal to theta, and we get A is equal to minus QE by M into theta. Now the relation between theta x and L is theta is equal to x by L. Substituting this value here, we get A is equal to minus QE by ML into x. Comparing this with minus omega square x, we get omega square is equal to QE by ML, or omega is equal to under root QE by ML. Therefore, the time period is equal to 2 pi by omega, that is equal to 2 pi under root ML by QE. This is our answer. Question number 11. We have to calculate the voltage induced across a solenoid, which is given by L di by dt, which can be written as L delta I by delta t, where L is the self-inductance of the solenoid, which is equal to mu naught n square A upon L into delta I by delta t, where n is the number of turns, which is equal to number of turns per unit length, small n, into L length. Here it is 10 turns per centimeter into length 0.5 meter, that is 50 centimeter. So this is equal to 500 turns. Therefore, putting the values, we get the induced voltage as mu naught is equal to 4 pi into 10 to the power minus 7. N square, that is 25 into 10 to the power 4. A is 1 centimeter square, that is 10 to the power minus 4 meter square. L, that is 0.5 meter. Delta I by delta T, 2 minus 1 upon 0.1. This comes out to be 2000 pi into 10 to the power minus 7 volt, as these cancel each other, is equal to 2 pi into 10 to the power minus 4 volt, which is equal to 6.28 into 10 to the power minus 4 volt. In the optional question, we have to calculate change of magnetic flux through a coil, that is delta phi is equal to phi final minus phi initial. Phi final is equal to 0 minus NBA. Putting the values, we get minus 140 into 9 into 10 to the power minus 2 Tesla. To area is 5 centimeter square, that is 5 into 10 to the power minus 4 meter square. It comes out to be minus 6300 into 10 to the power minus 6 wavers, which is equal to minus 6.3 into 10 to the power minus 3 wavers. Now part B, induced EMF is equal to 0 because the coil is quickly removed out of the field region. For question number 12, we will have to redraw this circuit. This is 3, this is 3, this is 2, this is 1, and this is 2. The equivalent can be redrawn like this. 3 and 3 becomes 6, 2 and 1 in parallel becomes 3, and this is 2. Since 6 and 3 are in parallel, their equivalent will be 6 into 3 upon 6 plus 3, that is 2 microfarad. So equivalent circuit now can be redrawn as this. 2 and 2 in parallel, their equivalent is C equivalent, that is 4 microfarad. Total energy stored will be half C equivalent V square, that is equal to half to 4 into 10 to the power minus 6 into 10 to the power 4 volt, equal to 2 into 10 to the power minus 2 joule, that is equal to 0.02 joule. In question number 13, again we have to solve a circuit. These three resistors, 2 ohm, 4 ohm and 2 ohm are in series, so their equivalent will be sum of these, that is 8 ohm. This 8 ohm and this 8 ohm are in parallel, so their equivalent will be 4 ohm, and the equivalent circuit can be drawn like this. This is 4 ohm, this is 2 ohm, this is 2 ohm. These three resistors are again in series, so their equivalent resistance will be their sum, that is 8 ohm. Current is equal to V by R equivalent, that is equal to 16 volt upon 8 ohm, that is 2 ampere. This 2 ampere current from the battery will distributed at this junction. Since these two resistors are equal, they will equally distributed 1 ampere and 1 ampere. This is 2 ampere. So the current through this 4 ohm resistor is also 1 ampere, and hence voltage drop across this resistor is I into R, that is 1 ampere into 4 ohm, that is 4 volt. Question number 15, part B. VRMS is equal to given by VR square plus VL square, that is equal to under root 160 volt square plus 120 volt square, that is equal to under root 25600 plus 14400 volt, that is equal to under root 400 volt, that is equal to 200 volt. The effective current, which is also called IRMS current, is given as 1.0 ampere. So the total impedance in the circuit Z is given by VRMS upon IRMS, that is equal to 200 volt upon 1 ampere, that is equal to 200 ohm. In the optional question, This is optional question. Since the current is ahead of the voltage, Y must be a capacitor, and we have to calculate the RMS current. Know that Xc upon R is tan phi, that is tan pi by 4, which is equal to 1. This implies that Xc is equal to R is equal to 100 ohm. So Z is the total impedance is given by Xc square plus R square, that is 100 root 2 ohm. Using root 2 is equal to 1.41, it is equal to 141 ohm. So IRMS current is given by VRMS upon Z. VRMS is given as 141 volt upon 141 ohm. This is 1 ampere. Now I am going to discuss question number 17. We are going to study reflection of a converging beam of light at this convex surface. We are going to use the formula N2 by V minus N1 by U is equal to N2 minus N1 upon R. Since the light rays are going from air to glass, N2 is 1.5 upon V minus N1 is 1 for air. U, all these distances are measured from this point. In the direction of incident ray positive and in the opposite direction negative. And here is our object, which is a virtual object, which is a very crucial point in solving this question. So our object distance U is equal to plus 20 centimeter is equal to N2 minus N1 0.5 upon R for a convex part is positive, that is 5 centimeter. So it can be written as 1.5 upon V minus 1 by 20 is equal to 0.5 upon 5, and this can be written as 1 by 10. So 1.5 upon V is equal to 1 by 10 plus 1 by 20 is equal to 20. 2 plus 1, 3 by 20. This implies that 3V is equal to 1.5 into 20, that is equal to 30. This implies that V is equal to 10 centimeter. Plus sign shows that the image is real. The ray diagram can be drawn like this. Here are the normals N1 and N2. So the rays will bend towards the normal, that is like this and this. So this is our image, this is our object P, this is our image I, and the image is formed at the surface of a sphere. This is very important point, and this distance is 10 centimeter, which is equal to diameter of the sphere. In the optional question, we are going to discuss reflection at a concave surface. Again, we are going to use N2 by V minus N1 upon U is equal to N2 minus N1 upon R. Here the light, here is our object, and light is going from glass to air. So N2 is 1 upon V minus 1.5 upon U. So U is the object distance. All the distances are measured from this point. In the direction of incident ray, positive, and in this direction, negative. So our object distance is negative, and it is equal to diameter minus 20 centimeter is equal to N2 minus N1 minus 0.5. R for a concave part is negative minus 10 centimeter. So it can be written as plus 1.5 upon 20 is equal to 0.5 upon 10. Can be written as 3 by 40, and it can be written as 1 by 20. So 1 by V plus 3 by 40 is equal to 1 by 20. This implies that 1 by V is equal to 1 by 20 minus 3 by 40. 42 minus 3 upon minus 1 by 40. Implies that V is equal to minus 40 centimeter. Getting sign shows that the image is virtual. And draw the ray diagram. Here is our object O. This is the normal. Light ray will bend away from the normal, and after producing backward, they will meet here, and this is our image. And this distance from point P is 40 centimeter. Question number 19, part B. This is not a problem. It is a conceptual question. It is based on the concept that emission of electrons takes place only when energy of a single photon is greater than the work function. But here, energy of single photon is less than work function, so emission of electrons will not take place no matter how many photons are incident on the metal surface. Kmax is equal to E times stopping potential, that is 1.6 into 10 to the power minus 17 coulomb, 1.5 volt, that is equal to 2.4 into 10 to the power minus 19 joule. This is our answer. In question number 21, part B, answer is no. Part C, we have to calculate magnetic moment, that is IA, that is equal to minus E charge upon time into A, and time period is given by 2 pi r upon V, and area is pi r square, so it becomes minus EVR upon 2 multiplying M to numerator and denominator, it becomes minus E by 2m into MVR is orbital angular momentum L. So mu becomes minus E by 2m into L. So this is the expression for magnetic moment on an electron revolving around the nucleus like this. Now I am going to discuss question number 24, part B. Polarizing angle is same as the Weierstrass angle, and relation between the Weierstrass angle and angle of reflection is IB plus R is equal to 90 degree. This implies that IB is equal to 90 degree minus R into 90 degree minus 30 degree, that is equal to 60 degree. The effective index is given by tan IB, that is tan 60 degree, is equal to root 3, equal to 1.73. Question number 25, part A. Interference pattern cannot be produced by two independent monochromatic sources of light because the phase difference delta phi between them is not constant. Part B. The distance of point P from O, x, is given by beta upon 3, where beta is the fringe width, and given by lambda capital D upon small d. The path difference at point P is given by d sine theta, where theta is this angle, and tan theta is given by x by d, which is equal to theta, which is equal to approximately equal to sine theta, if theta is very small. Therefore, the path difference becomes dx upon capital D. Putting the value of x from here, we get a small d upon capital D, lambda capital D upon 3 times a small d, and it becomes lambda by 3. The phase difference corresponding to this path difference is 2 pi by lambda delta x, that is equal to 2 pi by lambda into lambda by 3, that is 2 pi by 3. So I is given by I naught cos square delta pi by 2, that is equal to I naught cos square pi by 3. Cos pi by 3 is 1 by 2, therefore I naught 1 by 2 whole square, that is equal to I naught by 4. Part C. Let x1 be distance of fifth bright fringe from point O, which is given by 5 beta. Let x2 be distance of second dark fringe from point P, which is given by 3 by 2 beta. Therefore, delta x is equal to x1 minus x2 is equal to 5 beta minus 3 by 2 beta, that is equal to 7 by 2 beta. Putting value of beta in terms of lambda capital D upon a small d, we get this. Therefore, lambda is equal to 2d delta x upon 7 capital D. Putting the values, we get 2 into 0.5 mm, that is 10 to the power minus 3 meter. Delta x is 4.13 mm, that is into 10 to the power minus 3 meter, on 7 into d is 1 meter. We can write it as 0.59 dividing by 7, so it becomes 0.59 into 10 to the power minus 6 meter, that is equal to 590 into 10 to the power minus 9 meter, that is equal to 590 nanometer. In the optional question, part B, the width of the central maximum for a diffraction pattern is 2 lambda d by a, where lambda is the wavelength, d is the distance of the screen from the slit, and a is the slit width. If monochromatic yellow light is replaced with red light, it means wavelength increases because wavelength of red light is greater than wavelength of yellow light, and hence delta x increases. Similarly, if distance between the slit and the screen, that is capital D, is increased, delta x increases again. Using the same setup, same wavelength, and same screen to slit distance, 10 interference fringes, which is equivalent to 10 beta by 2 distance, is found within the central maximum of diffraction pattern, whose width is 2 lambda capital D upon A. This implies that 5 lambda capital D upon a small d, which is equal to fringe width of interference pattern, is equal to 2 lambda capital D upon A. This implies that 5A is equal to 2D. This implies that A is equal to 2 by 5D, that is equal to 0.4D, that is equal to 0.4 mm, since D is 1 mm. Now I am going to discuss question number 27, part B. X-axis, this is y-axis. Here is a small current element IDL, and we have to find magnetic field at this point. This is R vector, position vector. According to Bayes-Sawart law, magnetic field will be given by mu naught by 4 pi IDL cross R upon R cube. Since IDL and position vector R, they are mutually perpendicular, the magnitude of magnetic field will be given by mu naught by 4 pi IDL by R square. Putting the values, we get 10 to the power minus 7. I is 10 ampere, dl is 1 centimeter, that is 10 to the power minus 2 meter, R square 0.5 meter square. So it comes out to be 4 into 10 to the power minus 8 Tesla. Part B of optional question. Since this point is on the axial position to the straight conductors, magnetic field due to the straight conductors at this point will be 0. So only magnetic field at this point will be due to this semicircular part, which is given by mu naught I by 4R. Putting the values, we get I is 5 ampere upon 4, R is 2 centimeter, that is 2 into 10 to the power minus 2 meter, which is equal to 4 and 4 get cancelled. 5 pi by 2 into 10 to the power minus 5 Tesla, that is equal to 7.85 into 10 to the power minus 5 Tesla. Thank you very much.